Okay, yes. Great. So this is about social aspects of sustainability, and that's where I'm going to try and keep this presentation oriented. And today I'm going to be talking about district energy for resilient local energy economies and industries. So buildings are a really important place to talk about when we're talking about sustainability. They consume about 40% of primary energy resources consumed in the United States each year. And those come from fossil fuels like petroleum and coal, as well as renewable energy. And the US consumes a lot of energy, about 100 quadrillion BTUs per year. These renewable and non-renewable sources go to produce electrical power, and then they go to end-use sectors, including transportation, industry, residential sector, and commercial sector. And so that energy is either directly going to these end uses, or it's going first to create electricity with losses, and then to power those sectors. Buildings, homes, and businesses in the residential and commercial sector contribute about 12% of the nation's greenhouse gas emissions. And a majority of those emissions are associated with energy consumption. You can see the orange line is the upstream emissions coming from electricity that's used in the homes and buildings. And the blue line are the direct emissions, and most of those are coming from heating and cooking. And you can see over time that there hasn't been a lot of change in the direct emissions. This has been a very difficult area to reduce the emissions of, and so it's a really critical place for research to occur. There's a lot of ways that you can quote unquote green a building or lower the carbon emissions associated with that building. In new buildings, this is often seen as designing for sustainability. So they can be more energy efficient, or they can use renewable energy sources. Or in older buildings, you can look at the retrofitting of those buildings, as well as the use of more efficient appliances. So in the sake of coronavirus era, I am without childcare, so my kid is going to be here. Hey, I'm on a meeting right now, okay? I'll come and get you in a bit. So that's going to happen maybe once or twice. So these are really important technologies, but at the same time, we're faced with a really pressing, urgent change in climate. And there's also new science coming from smart meter data and climate change projections that are starting to help us understand who's going to be most exposed to these climate impacts. And a recent study as of May 2020 found that heat increasing in just an area close to home for here, we're in Berkeley, California, in South Los Angeles, is going to disproportionately affect disadvantaged communities who not only don't have the finances to purchase some of these more expensive green technologies, they also don't have the ability to move to other locations away from the most extreme effects of climate change. So we're faced with a real issue when we talk about equity in sustainability. It's not just about pushing people to use less energy by making them pay more, or having very expensive green technologies that are out in the market and then we somehow hope these are going to be deployed. It's about really lowering exposure of the most vulnerable communities to climate drivers. And this is an area that I'm very passionate about, and I find very fascinating to look at where the opportunity for not only social politics can come to play, but also technology solutions. So in general, people in poor neighborhoods are going to be more exposed to climate change health threats. And these people are also the ones who probably have less access to healthcare. And we've seen this in the pandemic, the disproportionate amount of people who are affected. So this is what I'm going to talk about a little today for this session, is about how you can have access to not only energy efficiency, but reliable and resilient technologies for providing energy services. So can we turn this race to net zero carbon into a bigger opportunity to reimagine urban services? So if we're just talking about focusing on lowering emissions and energy efficiency, I'm finding a lot of these projections of what should happen are really looking at an urgency on compliance and adoption of better technologies, or drop-in technologies to what we already have, like hybrid vehicles. And those are very important solutions, but there's a lot more to it to improve a community and create social equity in sustainability. Examples come from mixed-use developments and designing urban areas so that you don't have to drive as much. Improving local quality, so making sure the technologies you deploy don't create odors, aren't noisy, look appealing. Life cycle impacts, so you deploy a technology, but you're not going to affect someone in manufacturing or downstream in recycling in a way that you didn't account for. Leveraging and protecting regional energy sources and making sure you understand the local impact of your technology solutions. Making sure that there's space for resilience in the community, which means making room for urban food systems, such as having rooftops open for growing food. And then finally, close engagement of users in service. We've found these local energy economies where the people who are getting the energy service are also the ones very intimately associated with the resources and the technology, are all communicating and educated, and ultimately take energy service as part of their identity. They have a pride in a green community. And where does industry fit in all of this? We can talk about the industry in a community, some big manufacturing company as being a challenge in the face of greening, or a liability. They're a source of pollution. They can leave right away if a pressure comes on. Or we can talk about what are the technology solutions that can engage that industry, make them a part of the community, make them a source of green jobs. So there's a lot of ways that these pieces can come together. And today I'm going to talk about district energy, which I think has potential to bring these pieces together in very interesting ways. So district energy is a proven technology. It basically, you have your facility that generates thermal energy. It's used to make steam or hot water or chilled water. That energy is then passed through a network of pipes to buildings. And those buildings take the energy and share that service rather than having their own individual boilers. In some systems, this can be called combined heat and power, where you not only create the thermal energy, you're also creating electricity. And this becomes a very resilient system, an efficient system, because you're not focused on a grid very far away and upstream that might be susceptible to wildfires or power outages. You have a very local system and you know the resources. There's also an opportunity to bring in waste heat sources and sources of waste biomass that can bring in local industries. And district heating and cooling has changed a lot over time. It's a very old technology. And as you see in this figure, the energy efficiency of district heating has improved substantially as we've transitioned from a steam system run on coal now to systems that are hot water, that are trying to create as little of a difference in temperature as possible between what's needed and what's served. And you can use many different heat sources to achieve this. Cost savings have been demonstrated in many different end uses. And so there's a really compelling drive now to look at these modern district systems for community service. There's also fascinating aspects around district energy for their ability to provide this shared sense of energy. This is a very cool project. I think it's in Alberta, California, and they use solar energy to actually charge underground where their thermal reservoir is, so that during the winter time, they can actually use that excess energy and provide their heat. So this is really interesting to talk about sharing thermal energy storage at scale, not each home having its own battery. There's also economies of scale that come from having these large systems. Sure, it's a very large upfront capital investment, but you can apply better, let's say, air quality emission technologies at the facility generating the energy in a way that you couldn't possibly imagine doing at a single building. There's also district energy solutions for both brand new developments and existing infrastructure. I think it's amazing, this system in downtown Phoenix, how over just a few years, they've been able to add on more and more buildings with one central system. And so the economics of expanding a system to a new building, or maybe a building that just has an increased need for cooling because of changing climate, is possible. So there's also some challenges. District energy largely remains a solution for campuses in the United States, and over 90% are powered by fossil fuels still. So you see here, these are the additional floor space in the United States served by district energy systems. And campuses are in green, like schools, hospital, institutions. You have very little change over time in the amount of residential sector coming in. And this isn't the case all around the world. It's the case in the United States primarily. If you look at these different countries that have a long history of using district energy and cooling, you see they're using recycled heat, direct renewables, and some fossil fuels in gray predominantly. Finland, for example, is driven by district energy because they have so much of this recycled heat from the paper industry and from their timber industry. And despite there being over 900 systems in the United States, it's not commonplace in the minds of Americans. And that's going to create a challenge when communities are coming together to talk about what are the possible options for a green world. District energy is not gonna come into the conversation. You look at these systems, they're predominantly in colleges, downtown utilities, military, and the trend that I see here is that there are single users and operators who are seeing the benefits. Even if, let's say, many students on a campus are benefiting, they don't understand where their energy is coming from. It's going to be the campus who gets the benefits. And so in my mind, I see this as a real challenge, that there's no community identity in this. It's not multi-stakeholder. And in general, we have this issue in the United States that there's not a lot of community identity in your utilities. And I think that's changing, and that's an opportunity that can be leveraged in a big way when we start talking about sustainable communities. And there's a lot of opportunities for district energy to play a role here because a lot of the end uses for energy in buildings are not easily electrified, which means you can't just switch it from natural gas or fossil fuels to electricity so rapidly. You have a lot of homes, you might have the home yourself that's heated with a wall heater that runs on natural gas. And there's a lot of systems in industry that really, really fit well with the high temperatures required for their processes with steam. And so when we look at what's been happening in the last few years, a recent report, a 2019 Congressional Report, attributes growth in district energy sector to two primary factors. One is expansion in traditional markets. That might be campuses, military bases, airports. And the other is this sustainable city initiatives, renewable energy standards, and the need for resilience in new markets. And when I was looking through the literature and at different reports with the support of IDEA, the International District Energy Alliance, we found that this second point is very hard to validate. There's a lot of qualitative information, but there's not really a lot of quantitative information. And from a research perspective, this is an area for improvement where you need metrics and validation to be able to go to communities and demonstrate that these systems don't just work on campuses, they also can work very well for communities. So when we went through different proposals for projects that might be coming on the line in the next 10 years, looking at these drivers, you can break them into a few groups for simplicity. You can talk about the energy supply conditions. Do you have a lot of resources, thermal resources on hand in the area? You can talk about energy demand conditions. Do you have the right density of buildings that could benefit from this district energy? Do you have policy conditions that would incentivize the use of regional energy resources or community sharing? And then do you have that drive, that local energy economy with real stakeholders who are invested in making this happen? Just as a few examples, I found this one really interesting. This is the Nashville airport had a quarry nearby, and this quarry got flooded and started flooding the community. And it wasn't until that flood that the airport realized they could actually leverage this and use that deep water cooling for a district energy system to power their airport. So there was a new energy supply and the right incentives to make it work. On the other hand, you have growing cooling needs in downtown Phoenix, which has led to a very, very successful district energy system and its expansion. There's substantial amounts of cooling and there's new developments in the area. So the complexity of this is real, and there's a lot of pieces that there's some qualitative pieces, there's some quantitative pieces, but if you break these down further into what are the drivers for different scenarios of deployment, you can start to see some trends. And what we found is that you can break expansion of district energy into new projects, brand new developments of district energy, into expansion projects. So you have an existing system and you're expanding it, and modernization projects, which I view as retrofitting of the system. Maybe it only provided thermal energy and now it's going to provide electricity, or maybe you want to make it more sustainable, and instead of using coal, you might use biomass. And so you start to see some of the factors are across the board going to be beneficial: zero carbon goals, new energy resources, increased cooling loads. And then you see some that are very, very specific to one scenario. For example, a brand new system in a local energy economy really requires an understanding of who you're displacing, what the utility support might be for this system, and how this is communicated to the users. So in my research, I work with a number of people at the lab, and we coupled this project looking at district energy system drivers with another project that was done for the California Energy Commission that looked at the ability for mixed-use developments, which means a mix of residential, commercial, hospital, other types of floor space. The growth of floor space and need for these buildings in California, we looked at areas in California where there was a high likelihood of these mixed-use developments being generated by 2050. And then we tried to understand whether there was an overlap of drivers where there would be potential for district energy to serve those systems. So what we did is we looked at a modern district energy system that uses what we call CHP, combined heat and power, so providing electricity and heating and cooling to these buildings, and we compared it with the fossil fuel option, where you have a grid coming in providing electricity, and you have individual buildings with their boilers in the basement. We also compared this with a renewable scenario, so we wanted to understand what the benefit would be if instead of using heat pumps based on renewable electricity, we use this district energy system. We also looked at the opportunity for using the growing amount of bioenergy in California. And so for a brand new system, we considered, well, let's just say there's an ability to tap into a resource that looks a whole lot like natural gas. So this is kind of the drop-in technology where you have just natural gas pipelines and you can leverage it. And through policy, you can get credits for using bioenergy that's been injected into that pipeline. Or if it's a brand new development, you could talk about a community co-locating that district energy system, that new mixed-use development, and some system to take the waste, let's say your garbage, your food waste, or your local agriculture waste, if you're in the Central Valley, and convert it into energy on site. Now, there's a lot of problems with trying to propose this in a community that's established. Some of these facilities might be noisy, they might be smelly, but if you have a brand new facility, you might be able to design it in a way that makes more sense and doesn't have these local impacts on the community. There's also then the classic case of the expansion of existing district energy systems. So we looked at that. We looked at, well, we've got a community with a district energy system. We have a number of them in California. And then we said, well, what's the economics look like for just expanding it to a new community, like let's say a multifamily house. There's other examples for modernizing, and we're starting to see proposals coming in for, this is downtown Pittsburgh, actually where this conference was originally going to be held. They have a number of systems, and there's some real interest in creating more of an energy sharing situation. And I think this is really fascinating. We talk about shared service economy where you have Lyft and you don't own your own car. Maybe we can get people to start thinking about this for energy too, where you're sharing resources, and instead of these 4 blocks being totally separate networks, they actually tap into each other and create a more resilient system. In the same vein, there's also the ability to modernize a system through fuel switching. And so we looked at that. We said, okay, you've got this traditional system that's using fossil fuels like natural gas, and now you're going to switch it over to a renewable resource. There's also modernization where you didn't provide electricity originally, and now you're going to switch it over to combined heat and power. So we looked at the cost of this, and I'm going to show some results for the Bay Area. So you see this is amortized annual cost in $1 million, and the point shows the net, and these lines show the profile of the cost. So this is coming from, this is heat pump electricity in this renewable energy scenario. So here we have renewable energy powering heat pumps. We show labor, we show the sales, which would be the revenue, and then we compare that with the fossil fuel case. And you can see from the net that the renewable heat pumps is going to cost more than the fossil fuel system. Then when we compared this to our district energy systems, and these are all brand new systems, we found that this is biogas, where you aren't cleaning it up and you have a local facility generating it. Biomethane, where you just tap into the natural gas pipeline and you're paying for the renewable energy credits. Or syngas, which is a mix of kind of hydrogen and carbon monoxide that's generated from the gasification of very dry biomass. So these are just technologies for making bioenergy. And we look at the cost profile, and we find that based on the price that we assume for this, this fuel, you can actually get substantially better numbers than the fossil fuel system. You can also get higher, and you can also get higher, a little bit higher than the renewable case at the highest fuel price. So this is a really interesting analysis because it's starting to demonstrate not just we know policy is important, but how important is it? How important is it? What's the difference between being better than renewables or fossil fuels? And then finally, we looked at, instead of using a spark ignition gas engine for these systems, we looked at a fuel cell, so a bit more modern for the combined heat and power facility. And so that also gave us some new results on not only the policy aspect, but the impact of technology. We looked at 5 different areas: the Bay Area, the Central Valley, Los Angeles, Northern Central Valley, and San Diego, where we expected these mixed-use developments to be very viable. And we looked at the case for what we call expansion. So not just a brand new facility, but an existing facility that's going to be modernized or expanded. And so here you can see there's also cases where you can be negative and cases where you can be positive. And it is dramatically different based on the need for energy in these different regions. Each of these different systems provides the same amount of electricity and heat in one location, but then across the different locations, we found very different sizes of district energy systems were going to be needed. So the Bay Area is a mild climate. It had actually the smallest system, and then some of the largest systems were in Central Valley. So this was a very interesting analysis to be able to combine not only just one location, but to start generalizing what our findings are. And so what about new district energy systems in existing communities? So far we've talked about largely brand new systems. Well, this is a very challenging piece to bring in because a district energy system requires digging up the ground, putting in the pipes, and that's disruptive to traffic. And it also might be having to maneuver around the location of buildings that aren't designed for district energy. So it's more costly, but we were able to do an analysis of viability based on clustering of buildings. And over time, we looked at, well, what are the types of buildings? And this this table here shows you, well, if you have a health building, that's actually quite a good load, a good energy customer for a district energy system. It has a high cooling load, has a high heating load. And based on these rankings, we were actually able to look at the buildings throughout California over time. We developed a building stock turnover model, which means you project construction and demolition of different buildings that you have, and based on economic drivers and population, what the potential buildings might look like in the future. And so this is a lot of information, but this shows in the Bay Area out to 2050, what the different types of buildings might be. And then we highlight in blue these neighborhoods or districts where there's enough demand for this thermal energy where a district system should be considered for that community. And so what's in the pipeline? What are the big messages here? we find that there's a lot of key benefits for district energy systems that have already been demonstrated in traditional markets. And this is also true for just combined heat and power systems in general and microgrids. And that comes from energy surety, knowing what you're going to get when your investment, economic value, knowing that this is going to create cost savings over a long period of time, sustainability, knowing that you can create a low carbon future, and resilience, knowing that you are able to provide power in the face of outages or unexpected disruptions. So all of these we find appear to be drivers also for communities, but there are clear barriers that are affecting this deployment. One of those, as I've mentioned before, is just helping increase the profile in the minds of people of district energy and the services it can provide. One key way to do that is to do these cost assessments and help people understand exactly what these drivers look like. Another is really creating new incentives for overcoming this upfront infrastructure. This is large infrastructure, and if you're building it in a location where there are no buildings, you have no buy-in yet. You don't know who your customers are going to be, and that is a very high risk to ask someone to take on. So there's some challenges. And also district energy is not going to work everywhere. We have communities in California that are high risk of wildfires. These are in rural areas and in forested areas. And district energy is probably not going to be the solution for them to become more resilient communities. They're just too far apart for it to make sense and be cost effective. There's also, as I mentioned, a lack of innovative project financing already out there, even if there have been many, many demonstrations of these funding concepts over time in the conventional markets. So I think there's a translation that needs to happen into the community space. And then finally, there really needs to be this coupling of viable technologies and end uses, demonstrating it and having these early market adopters really push the value. And this is a very cool system. In my mind, it's CalMax Ice Bank, and it shows how you can create ice when the sun is shining and then use that ice later, all sorts of thermal energy storage to help you buffer those uncertain times and create a more resilient system. And so just to end, I'll say that in this findings, I've largely found that the key will be inclusion of communities and industry stakeholders in research projects driven by established actors who are very familiar with these highly complex systems in district energy and demonstrate the scale and return on investment. And so this is a long process to get community buy-in, but I believe like over time, the value of this is going to create more long-term benefits in terms of CO2 reductions and resilience. And so we talk about the urgency of getting to carbon neutral by 2045. That means we have to start this process now if it takes 15 years for community buy-in and deployment and operation to successfully happen. And with that, I will open it up to questions. Thank you, Julie. Oh, thank you. My last slide. I'll thank some of the people are already on here. Rapp, Alastair Robinson have worked with me a lot on this. IDEA partners, Lakshmi Rao is on the call, Jackie Kinson and Robert Thornton. And this was funded by the Advanced Manufacturing Office with the Department of Energy. And some of the work I presented was with Sarah Smith and Corinne Scown with the California Energy Commission project. So thank you.